Let's discuss hexagonal close-packed structure. Hexagonal close-packed structure consists of arranging identical spheres in a single closest packed structure as each atom is in contact with 6 other atoms in that layer. Okay, this is the first layer. This black spheres are in first layer. Let's consider that first layer. Each atom in that first layer is in contact with 6 others in that same layer. Okay, so this is 1, 2, 3, 4, 5, 6. This atom is in contact with the 6 others. Okay, so this is extending up to infinity. So each atom is in contact with the 6 others in this single layer. A similar layer, this layer is known as B. Sorry, this layer is known as A, and a similar layer B I have drawn in this green ink. The similar layer B is placed over the first layer as each atom, each sphere is in contact with 3 other spheres in the first layer. Okay, and a third layer, this green layer is also extending. This green layer is identical and the green layer is similar to this first layer, and this is also extending up to the end of the crystal. Okay, and a third layer is placing, and a third layer, the spheres in the a third layer is placed directly over the centers of the spheres in the first layer. Okay, so that arrangement is known as AB stacking. AB stacking. The third layer is placed directly over the centers of the spheres in the first layer, that is ABA. Okay, and let's visualize this in a 3-dimensional manner. So in this figure, this is the layer A, and this green one is the layer. The green layer is belong to green spheres is belong to the layer B, and this is also an identical layer is placed directly over the first layer. Okay, so this is ABA stacking. ABAB stacking. ABAB stacking. Okay, and these are the lattice parameters A, B, and C. Okay, so the lattice parameter from here to here, the lattice parameter A, from here to here, the lattice parameter B, and A equal to B, and that is not equal to C. Okay, that is not equal to the third lattice parameter C. And the angle between A and C, as well as B and C, is alpha and beta, that is equal to 90 degree, and the angle between A and B is gamma, and that is equal to 120 degree. Okay, so this is the arrangement. This is the hexagonal close-packed structure. Now let's examine the number of atoms as well as the coordination number, etc. Okay, the number of atoms in the unit cell, or number of atoms per unit cell, is equal to, look at this figure, each atom at the corner of this hexagon shares by other 6 unit cells. Okay, so 1/6 portion of this atom is there inside this unit cell into 1, 2, 3, 4, 5, 6. There are 6 atoms. 1/6 into 6 plus the same thing happens in the bottom layer also. So 1/6 into 6 plus half portion of this atom is there inside this unit cell, and half portion of this atom is also inside this unit cell. So half into 2 atoms, 2 plus another these 3 atoms are there completely inside the unit cell, that is equal to, so the number of atoms per unit cell equal to 6. Okay, next let us find out the coordination number, that is the number of nearest neighbors. For that, let's take one atom in this layer A, as the reference atom. Okay, that reference atom is in contact with other 6 atoms in the same layer. Okay, 1, 2, 3, 4, 5, 6 atoms in the same layer. So the coordination number is equal to 6 plus the 3 atoms on the layer B. Okay, this atom is in contact with this 3 atoms in the layer B. So 6 plus 3 plus on the other side there are also 3 atoms is in contact with this reference atom. So that is equal to 12. The coordination number is equal to 12. The number of nearest neighbors is the coordination number, and that is equal to 12. And the nearest neighbor distance, distance is equal to, these are the nearest neighbors. These two atoms are nearest neighbors. So the distance to R is equal to the lattice parameter A. Okay. So the nearest neighbor distance is equal to A. And next let us find out the second nearest neighbor, number of second nearest neighbor, second nearest neighbors. Okay, the same atom, let us take as the reference atom. So this one, and this all are first nearest neighbors, and the second nearest neighbor atom, one second nearest neighbor is this one, and another second neighbor is on the other side. Okay, so the number of second nearest neighbors is equal to 2, and the second nearest neighbor distance, is equal to, the distance between these two atoms is equal to C. And there is one ratio between the lattice parameters. C by A is equal to under root 8 by 3 is equal to 1 point is equal to C by 8.3. Okay, under root 8 by 3 is equal to 1.633. Okay. Volume of the unit cell is equal to area of this hexagon into height of that hexagon. Okay, that is equal to area into height, we know, that is C. And let us find out the area of the hexagon. For that, this is our hexagon. So there are six rectangles. 6 rectangles contributes to this hexagon. So first let us find out the area of one equilateral triangle. Okay, 6 equilateral triangles contributes to this hexagon, area of the hexagon. And let's find out the area of one equilateral triangle, AAA. Okay, so when we are considering that area of that triangle, area equal to half into base into height. Okay, so each side is A, and this distance is A by 2, and this is the height of that triangle. Okay, so that height we can find out, h equal to under root a square minus a square by 4 equal to root 3a over 2. Okay, root 3 over 2 is the height, and so area is equal to half into base is a into height is under root 3a over 2. Okay, so area, and that area equal to root 3 under root 3 a square over 4. Okay, under root 3 a square over 4. And there are 6 triangles contributes to the hexagon. So area of the hexagon equal to under root 3 a square over 4 into 6 is equal to 3 by 2, 3 under root 3 a square over 2. Okay, 3 under root 3 a square over 2 is the area of the hexagon. Okay, so volume of the unit cell equal to 3 under root 3 a square over 2 into C. The volume of the unit cell be equal to 3 under root 3 a square C over 2. The volume of the primitive unit cell is equal to, look at this figure. In this figure, this red shaded parallelepiped is the primitive unit cell of this hexagon closed active system. This kind of 3 parallelepiped contributes to the total volume of the unit cell. Okay, so volume of this primitive unit cell equal to volume of the unit cell, divided by 3 equal to under root 3a square c by 2. Okay, so this is the volume of primitive unit cell. Actually, primitive unit cell we define as the unit cell, with effective lattice should be equal to 1. Okay, effective lattice should be equal to 1. And next, let us find out the number of atoms. Atoms in a primitive unit cell. Number of atoms in a primitive unit cell is equal to. For that, we need to draw a hexagon. Consider an atom at this corner, and let me expand it. This is the primitive unit cell in 2 dimension. This is the primitive unit cell, and I am expanding this primitive unit cell. That means this 4 primitive unit cells share this atom. Okay, this 4 primitive unit cells share this atom. That means inside one unit cell, 1/4 portion of this atom is included in one primitive unit cell. Okay, this is in 2 dimension. In 3 dimension, there are 4 primitive unit cell on the lower side and 4 primitive unit cell on upper side. Okay, 4 primitive unit cell is there on upper side. So there are total 8 primitive unit cells. 8 primitive unit cells share one of the atom in the primitive unit cell. Okay, that means 1/8 portion of this atom is included in the volume of this primitive unit cell. So 1/8 into, there are 4 atoms at this layer, into 4 plus, when we are considering the bottom layer, 1/8 into 4 plus, and we need to consider this atom is completely inside this primitive unit cell. This atom belongs to the layer B, is completely inside this unit cell, and that is 1 equal to 1 plus 1 equal to 2. That means number of atoms in a primitive unit cell is equal to 2. Okay, so actually primitive unit cell we can define it as the effective lattice points inside this unit cell should be equal to 1, and we can ask how the effective lattice point is equal to 1 in this unit cell, because there are number of atoms in a primitive unit cell is equal to number of atoms in this primitive unit cell is equal to 2. Okay, for that, let me consider this figure. This is the layer A. This atom is belong to the layer A, and this atom is belong to layer B. Okay, I am drawing the side view of that 2 atoms. This is the side view of that 2 atoms. I am considering my lattice point is not at this point or not at this point. Okay, I am considering my lattice point at this point. That means I am considering the lattice point in between these 2 atoms. Okay, actually these 2 atoms are attached together. To show legibly, I have drawn like this. These 2 atoms are attached with each other, and the lattice point is there in between these 2 points. That means when we are considering this one and this green atom, that one lattice point is there, and this one and another green atom would be there on the top layer. So there is also one lattice point, and here also one lattice, here also 1/8 portion of the lattice point, here also 1/8 portion of the lattice point, and like that. When we are considering this figure, another green atom is there on the top layer. When we are considering this one, another green atom is there on top one. So that means the lattice point we are considering in between this atom and this atom belong to different layers. Okay, that's why we are getting the effective lattice point in this primitive unit cell is equal to, or primitive unit cell effective lattice point is equal to 1, but the number of atoms in that primitive unit cell is equal to 2. Okay. Now let's find out the atomic packing fraction. Atomic packing fraction. So there are 6 number of atoms is there inside this unit cell. 6 into volume of the volume of atoms in that unit cell. 6 into 4 by 3 pi r cube. Okay, 6 into 4 by 3 pi r cube over the volume of the unit cell is equal to 3 under root 3 a square c over 2. Okay, a square c over 2. That is equal to, we know radius of one atom equal to a by 2, or 2 are equal to a. So radius equal to a by 2, and c equal to or c by a equal to under root 8 by 3, and because of that c equal to 8 by 3, under root 8 by 3, 8. Okay, so 6 into 4 by 3 pi into a by 2 whole cube over 3 under root 3 a square over 2 into 8 by 3a. Okay, and that is equal to pi that is equal to pi over 3 root 2 equal to 0.74 or 74%.